In this video, we're going to consider various types of collisions and the momentum associated with each type, before and after. So we start with F net as ma, which we have seen as mdv dt, which is delta rho dt, time rate of change of momentum. So that's F net, and the mass can vary, the velocity can vary, or both can vary. Now make sure again that you don't confuse the time rate of change in momentum with the change in momentum, which is impulse. Very different ideas. Now, the first kind of collision is inelastic. It's probably the most simple and straightforward. We start with object 1 moving at speed v1, and it collides into object 2. In this case, we won't even have it move, and they stick together and move off at some speed v prime. That's the new velocity. So v1 prime, the initial velocity, the final velocity of object 1 is equal to the final velocity of object 2 for obvious reasons. They're stuck together. So since they're the same, we can drop the subscript and just call it v prime. That'll make it a little simpler. Conservation of momentum says that the momentum before and after is the same. So there's the momentum before, m1v1 plus m2v2, is m1m2v prime, since they're both masses are moving at this new velocity. Let's consider the kinetic energy. What happens to the kinetic energy? Yes, that's right. The kinetic energy goes down. And there's a really good reason for it. So let's graph it out. There's kinetic energy of object 1 to begin with. We have the collision, and the kinetic energy drops and then continues on. Why would that be? Well, most simply, consider the fact that kinetic energy is highly sensitive to velocity. Initially, it's wrapped up in m1v1, so it's less mass times this velocity, since this part is 0, is more mass times the velocity after. Well, the greater mass causes the velocity to go down to conserve momentum, and since kinetic energy is very highly sensitive to velocity, it gets decreased at a faster rate than the momentum, any momentum change. And actually, there is no momentum change right on through the collision. But nevertheless, the kinetic energy does change because the velocity is decreasing of the system. And even though the mass increases, the velocity increases more than the mass increases. Or the velocity squared, I should say. The velocity squared term. Okay, I think you've got the idea. So let me list the kinetic energies here. Initially, we had 1/2 m1v1 squared plus 1/2 m2v2 squared, assuming both are moving. After the collision, that will be K2. K2 is equal to 1/2 m1 plus m2 v prime squared. Now, if number 2 is at rest, it's called a Hooikeast, head-on inelastic collision with a stationary target. Hooikeast. Kind of catchy, huh? So that's just this momentum expression, before equals after, with this one crossed out. Now let's look at the ratios of kinetic energies. We can get a quantitative handle on the way in which they're related to each other. So after, 1/2 m1 plus m2 quantity v prime squared, and before, it's just this term because the second term is gone. Well, halves go away. And we recognize also from the Hooikeast expression we can solve for v prime, and that gives us this result, which we can sub in for the v prime in our ratio. And when we do that, we get the halves are gone, so we have m1 plus m2. The top part of this squared is m1 squared, v1 squared, and then we divide it by m1 v1 squared times this quantity squared, so there it is. And one of those goes away. And one of the mass m1s go away, and the v1 squareds go away. Ooh, I love when things divide out like that. So I have to make it all full and wonderful colors just to show the colorful expression of my heart at this moment that all those things divided out. And that gives us m1 over m1 plus m2. And that's a really useful result. It may be worth memorizing. Deriving it may not be quite as easy if you ever need it. But it kind of has a reasonability. K2 over K1. You know that afterwards is less than before. And what it ends up being is just the ratio of the masses. The ratio of the masses that are in motion. So the first mass in motion was m1. And then it's divided by just the combination of masses. So it seems reasonable that that ratio would give you the ratio of the kinetic energies. If not, memorize it or derive it if you need to. So again, if number 2 is at rest, m1 v1 equals m1 plus m2 quantity v prime. v1 prime equals v1 times the quantity m1 over m1 plus m2. Well, that's just simply the momentum of object 1 over the total mass. Now this probably has even more reasonability when you think of the velocity after the collision. Both masses moving, and since momentum is conserved, think of the total amount of momentum, which is momentum number 1. You know, velocity is going to have the dimensions of momentum over mass to get meters per second. So momentum over mass, but what mass are we talking about? Well, it's the total mass. So the velocity after the collision is corresponding to the total mass after the collision with the given amount of momentum, which is directly expressed by momentum number 1, v1 times m1. So that's a nice, useful result. Hopefully that makes sense. Now let's consider a semi-elastic collision. Now in any collision, total momentum is conserved. Now if it's semi-elastic, it's also semi-inelastic, so it's partly inelastic. What do you think happens to the kinetic energy? That's right, it goes down. Anytime you have an inelastic component to a collision, it's going to go down. And the simple reason is that the reduction in velocity is proportional to the increase in mass for the inelastic part of the collision. Well, since the reduction in velocity is proportional to the increase in mass, then you're squaring the velocity for kinetic energy. So that proportional decrease in velocity results in a greater amount of reduction of kinetic energy. So there you go. That was a fairly concise way of stating the reason why kinetic energy has to go down. But it's only for the inelastic part of the collision. Let's take a look at the kinetic and potential energy now, before, during, and after the collision. So we have the kinetic energy in object 1, and you have a collision, and what you notice here is that it drops, but then some of it comes back because part of it's elastic, and in the elastic part it basically pushes back against the other object, and so there's a loosely speaking, a springing back of some of the energy. And where was that energy? We'll look at that in a second. So this is the net result then after the collision. It's less. We have less kinetic energy than we did before. Corresponding to this, there is a potential energy curve. And this blue line is it. This is the potential energy curve. And the height of this is the same as the height of the minimum kinetic energy to the final kinetic energy value. They correspond. It's the amount you get back. Get it? So the amount of kinetic energy you get back corresponds to the amount of potential energy that was stored basically during the collision, and that had the ability to do positive work to increase the kinetic energy. And then this little part up here, what's that? Well, you never get that back. So that's a non-conservative force that's taking that kinetic energy away. That's friction, generally. And so that results in heat. Now we consider a force separation graph. For a collision like this, the force vertical axis, and separation. Let's consider this separation to be the distance between the center of masses of the two objects. Now that distance can never be zero, so don't expect this ever to go to zero. Let me show you what that would look like. There it is. And now let's look at how it progresses to form this particular curve. Here comes the arrows. During the collision, we have this part. During the first half and the second half, when it springs back, you've got the arrows going down like this. Well, you can imagine out here, the separation is large enough so they aren't in contact with each other. They first achieve contact right here, and then the force of interaction increases and gets higher and higher as the separation distance decreases. That makes sense. As you bring two objects during a collision closer together, if these are two automobiles, the bumpers give way with a certain force until the engine blocks meet and the frame and everything else, and the force greatly increases, and it can be a complex curve. So the force is increasing as the distance decreases. And this is going to be the closest the two objects ever come. The center masses will never achieve zero separation. That's impossible. So the center masses do achieve this much separation. That's the idea here. And then when the collision is fully manifested itself, essentially in the first half, done all the damage it can, there might be some potential energy stored in some elastic components that while this is taking away kinetic energy, this part increases the kinetic energy as it pushes back and increases the relative velocities of the objects. And once again, they separate on the way out if it's partly elastic. So the area under the curve on the way up, the force times x, that area all the way down to the axis, that's negative work. On the way back out this way, the area under this area is positive work, increasing kinetic energy. So the difference between them is this yellow area. So that yellow area represents energy that is lost to heat. Hopefully that makes sense. Now let's consider a perfectly elastic collision, in which case you conserve momentum as always and kinetic energy for reasons that you may surmise now from what my comments about the inelastic part of this kind of collision. If there is no inelastic part, then you're not considering a reduction in velocity with an increase in mass. You don't have to consider that for the elastic. Let's see how that works. So for momentum, we have the momentum of object 1 and object 2 equals the momentum of object 1 and object 2 after, or mass 1 and mass 2 after. All these terms are maintained in this expression, in this equation. For kinetic energy, we likewise have the four terms, namely the kinetic energy of object 1 and 2 before equals the kinetic energy after. Notice the velocity 1 prime and velocity 2 prime. Squared, of course. And these are maintained. These are not the same velocities because the objects bounce off each other. So they're not very, this is not all that simple. The givens that we have are mass 1, mass 2, v1 and v2. But what we need to find is the velocities 1 and 2 after the collision, and that's going to result in some messy equations. And I'm not going to take you through all that. You could do that as an intellectual exercise if you so please. So the results of that tedious algebra would look something like this. That v1 prime after the elastic collision looks like this. v2 prime looks like this. Now you see they're very, well, there are some similarities. I'm not going to try and give you some reasonability here, but notice both are divided by m1 plus m2. And v1 has v2 here and v1 here. v2 has prime has v1 here and v2 over here. Both m1 minus m2 in this part. So there's a lot of similarities, plus here, minus here. In any case, that's the results you should get from both conservation expressions simultaneously worked out. And an interesting result that comes from this is if you take v2 prime minus v1 prime, so you take this expression minus this expression, and notice that that is the relative velocity of the two motions, v2 prime minus v1 prime. It's how fast one moves with respect to the other. Well, it turns out that that is negative v2 minus v1. And v2 minus v1 is the relative velocity of the two objects before the interaction. Very useful. Can be expressed as v1 minus v2 as well. So the relative velocity before this one equals the negative of the relative velocity after the collision, which is this one. Now, let's look at the kinetic and potential energies. And so, for the kinetic, we have all the energy combined, and during the collision, we have a reduction, and then later on we see we get it all back. In other words, all the kinetic energy we had before equals all the kinetic after. Well, the corresponding potential energy function looks like this, essentially a mirror image, where there is no potential energy till the collision starts, and then you have a potential energy function that seems to mirror the kinetic energy dip. And in fact, the dip in kinetic energy, K lost, equals the amount of potential energy gained. And so that's really important. The gain in potential energy then, subsequent to this, is released into the additional kinetic energy. So you get it all back. All the energy lost in kinetic was stored in potential, and it's released back into the system to account for it all once again. So the force separation graph now has got a particular characteristic. If it's perhaps some complex relationship here between force and separation, as the first half of the collision ensues, we get a reduction in the position of the center of mass, the separation of the center of mass, and usually, often, not necessarily though, force being highest at the minimum separation. But then, for this to be perfectly elastic, the characteristics of the distortion in the material itself completely reverse themselves as they push back with the same amount of force at every particular separation distance. So, yes, you get the arrows going the other way, and they follow the same path back exactly. Let's consider a special case of an elastic collision. This special case is going to be a much simpler one. It's called the Hochwast, head-on elastic collision with a stationary target. So this is perhaps a complement to the head-on inelastic collision with a stationary target we addressed earlier. But this is elastic. And then V2 is equal to 0. That'll simplify our expressions for V1 prime and V2 prime. They now look like this. There's V1 prime, and here's V2 prime. Now notice they are both related to V1, which makes sense because there is no V2. Now these are a little messy to solve, but a whole lot easier to solve than the full elastic collision equations that did not have V2 equal to 0. And you might want to memorize these. But in any case, you don't necessarily have to. But it's not too hard because they're both multiplied by, related to V1, directly proportional to V1, inverse total mass. And the only difference then is that V1 prime is the difference between masses, and V2 prime is twice mass 1. Well, it's easy to say that, but if you're like me, it's still hard to memorize. But you're not like me. You're a lot younger, probably. And your brains are much more adept at grabbing onto information like this and hanging on to it with ease. So you go for it. In any case, another useful result is V2 prime is V1 plus V1 prime. Well, where does that come from? Where that comes from is that expression we had before, where the relative velocities before and after are equal and opposite. So if we think of bringing v1 prime over here, v2 prime minus v1 prime is the relative velocity before. I'm sorry, after. That's the relative velocity after. And then that's equal to the negative relative velocity before, which is v2 minus v1 with a negative, so that's just v1. So there it is. v2 prime is v1 plus v1 prime. Might be useful also. Another special case. And this time we have an explosion. An explosion is not elastic, but it has a particular characteristic. So we have M1 and we have M2. And when they explode, kaboom, there's a big bang. Not the big bang, but a bang. Hopefully it's pretty large, because small explosions are kind of boring. Bigger explosions, all the better. So after the explosion is done, M1 is moving to the left, M2 is moving to the right. Notice M2 is perhaps a little more massive, and as you would guess, the velocity is going to be less. These are not momentum vectors, these are velocity vectors. And they are in inverse relation to the masses, as you could surmise. So M1 V1 prime is equal to minus M2 V2 prime, because both befores, the conditions before, they are at rest. So there is no M1 V1 or M2 V2. So that's a pretty simple expression. We can solve for V2 prime, for instance, very simply, minus M1 over M2 times V1 prime. Now, let's do the kinetic energy ratios of an explosion. Well, it's the second one over the first one. And 1/2 M2 V2 prime squared over 1/2 M1 V1 prime squared. And I might have just misspoke, but this is simply the ratios of the kinetic energy of object 2 over object 1, not before and after. All of this is, they're both after, all right? So this is, the halves go away, M2, V2 prime, we just solved it here, M1, V1, they're both squared, divided by M2 squared, there it is, and divided by M1, V1 prime squared, so that's this. Well, some stuff goes away, so you know what that does to the condition of my heart. It makes it very light and happy. So once again, that's occurring. And we have K2 over K1. There is the result. Very simply, M1 over M2. Really simple result. Inverse ratio of masses is the ratio of kinetic energies. And last but not least, we'll consider a superelastic collision. So the kinetic and potential energy graphs, we have total energy in the system given by this dotted line. And here's the kinetic energy. Looks a little different. It's a different kind of animal. But there's a lot of animals in nature, so you shouldn't be surprised to see a different one than you've seen before. Here is the potential energy. Kind of looks like a mirror image, doesn't it? Sort of. And let's make sense out of that. Well, first we have U0. We have an initial potential energy, and that's has not been seen before, and that's the key to this phenomena. So the kinetic energy lost, as you can see from what it was, it dips down to here. So that's the kinetic energy lost. Then we have potential energy gained. So here's the potential energy initially. We gain this much. Looks like these arrows are about the same size, doesn't it? Yes, it does. Or pretty much so. And now we have the kinetic energy gained. So later on in the collision, we have the minimum kinetic energy rising up a lot to this final kinetic energy. So the kinetic energy gained is a significant amount, and the potential energy lost is likewise a significant amount from its peak down to the bottom. And of course, those concepts are related to each other. The potential energy lost is the initial potential energy, this, plus how much was gained. Here's how much is gained, and that equals the loss, because in the end, all the potential energy is released to give an increase in the kinetic energy. If you hear a funny noise in the background, my dog is chewing on a bone and licking her water over there, making a lot of noise and kind of being a nuisance tonight. Anyway, here's the force separation graph. In this case, it's going to operate a little differently. So now, watch the arrows. On the inbound, they're underneath, and on the outbound, they are above. So, what does that mean? Well, on the inbound, we have this negative work being done as force and displacement, as force and separation are opposite, essentially. Negative work reducing the kinetic energy. On the way out, we got work being done, positive work, that was greater than the negative work. The difference then is the gain in, well, mechanical energy is manifested in kinetic in this case. So the mechanical energy goes up equal to the area between the curves there, or yeah, between the plots. Basically surrounded by the path produced by those inbound and outbound arrows. So what's K loss? Well, K loss is U gained, as we just saw. K lost is how much potential energy is gained, because it's elastic, well, superelastic, but it has a regular elastic part to it. The potential energy lost, that's this, that's equal to the K gained, how much kinetic energy is gained, but the kinetic energy gained is greater than the kinetic energy lost. And for the simple reason, you probably have seen, that you have this initial stored potential energy, and it's released as well to give additional kinetic energy. Well, that's fantastic, and I'm sure you'd like to know if this really happens in nature, and I'm glad you'd like to know that, but you're just going to have to watch the next video, because this one has well exceeded my 20-minute limit. So we'll see you in the next video.